What is going on, everybody? Welcome to another machine learning with Python tutorial. In this tutorial, we're going to be talking about another supervised machine learning classifier, and that is the support vector machine, or SVM. Right out of the gate, you should think about what is support vector machine? What does this even mean? Well, first of all, machine probably just has some sort of relation to, like, it's a system or something like this. But then we have support what? Vector. So that should tell us that we're going to be dealing with vectors and in vector space. And then we see we have support, and we're not really sure what the heck that's supposed to mean. But generally, we're going to probably guess that it goes together. So we've got support vectors. We're not really sure what those are yet, but we'll figure it out. So we've got a support vector machine. We're looking probably for some support vectors, and we are recognizing that we're working in vector space. Okay. So the support vector machine was created by Vladimir Vapnik back in the 60s, actually, but went largely ignored and overlooked until the 90s. Vapnik was in the USSR at the time, and then in the 90s he got moved over to the United States, working with Bell Labs. And in the 90s, this is where it was shown that the support vector machine was better than the neural network at like handwritten number recognition and stuff like this. And then basically the SVM became the most popular machine learning algorithm for a while, and it's still one of the most popular machine learning algorithms. So first, let's just talk about the really high-level intuition of the support vector machine, and then we'll show an actual example of us using it, and then we'll break it down to explain how it does what it does, because it turns out the support vector machine, I would argue, is probably one of the most complex machine learning algorithms. So again, we're in vector space, so let's draw some vector space. And then the support vector machine is what's called a binary classifier, so it separates only into two groups at a time. But it's important to not confuse this with that a support vector machine can only classify into two groups. It just will separate two groups, or basically separate groups to really one at a time, one from the rest. I'll explain that more when we dive in, but for now, just understand it's a binary classifier, and what it wants to do is separate into two groups, and these two groups are denoted as positive or negative, and generally they're going to be a positive one or a negative one. So let's say you got two groups of data, so you've got some positives, so we'll draw positive, 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 and then you're going to have some negatives, so I'll draw a negative, negative, and a negative. And the objective of the SVM is to find the best separating hyperplane, which is also referred to as your decision boundary. So the best separating hyperplane or decision boundary that will separate this data. So for now, it's going to look a lot like a line, and I think that's why a lot of people can get confused, because the SVMs are always depicted, or usually depicted, in two-dimensional space, at most three-dimensional space. So the SVM is going to go, it's going to run, and it's going to say, I found the best separating hyperplane, and it is like this. Okay, and it would be a straight line if I could draw right. Anyways, so it's saying that's the best separating hyperplane, and it's going to say that is the best because the distance between that hyperplane and the associated data that it's separating is the greatest. So if you were to take a perpendicular bisector of the hyperplane and draw that to the closest data points, let's say you'd have like this, this, and this, okay? That distance is the greatest distance that you could come up with a separating hyperplane. So for example, another separating hyperplane might be this, right? That's a separating hyperplane. But the distance, again, the perpendicular distance between those is this and like, oops, this, right? Much smaller than our greenish-yellow counterparts, okay? So the support vector machine says that yellow-greenish line is the best separating hyperplane for our data. Now, how we get to that is another story, but for now, let's just remember that is let's say that's the best separating hyperplane. Once you acquire the best separating hyperplane, you can now take in unknown data. So let's say you have an unknown data point. So unknown u. Because that u rests on the right-hand side of that separating hyperplane, we're going to say it's not unknown. It's a positive sample. Conversely, if you had an unknown that was down here, it's not unknown. It's on the left-hand side of this hyperplane. Therefore, it's actually a negative sample. So that is the intuition of the support vector machine. We just need to find the best separating hyperplane, and then from there we can classify new data points. Again, I will just reiterate, it's a binary classifier, and natively we want it to be against linear data. So for example, what is the best separating hyperplane? Well, turns out we can't do that, right? Where is that hyperplane? Right? It doesn't exist. So in theory, you can't have one, but wouldn't it be nice if we could do like that, right? Everything that is on the left side of this line is a minus, and everything that's on the right side is a plus. So I'll leave it to you to determine whether or not that's even possible, and we will answer that question, I promise. But for now, let's actually apply the support vector machine in a more simple example. We're going to be using the same example that we did before with the breast cancer dataset. So let's go ahead and hop over there. Okay, so now what we're going to do is we're going to take the same code we used back in part 14 with the k-nearest neighbors algorithm. If you don't have that, go to the text version of this tutorial on pythonprogramming.net, and you can just copy and paste. It'll be right at the top. So here's the code. This is the code we used with the k-nearest neighbors. Now using the support vector machine, super simple. We're going to import support vector machine from Scikit-Learn, and then we're going to come down to the classifier, and we're not going to be using k-nearest neighbors. We're going to use svm.SVC for support vector classifier, and then we're going to use empty parameters there. There are a lot of parameters that we can modify, but in order to know what to modify or what it's doing, we need to break down the algorithm first. So for now, we'll just use the defaults, and let's go ahead and run it, because that's all we have to do. Super simple to change algorithms. So there we go. We ran it, 92% accuracy, and then this is the classification that we just kind of made up, and it did it right. Let's run it one more time. 92 seems kind of low. There we go, 96. Okay, so that is the support vector machine in practice. Again, all we did was just take the data, replace some of the data with some outliers, which later, now you'll see how different the support vector machine handles outliers as opposed to the k-nearest neighbors. What if we did not drop the ID column? So let's do that, and then we're just not going to make a prediction. So if we don't drop the ID column, we're relegated back to about 65% accuracy, so it does better than the k-nearest neighbors did when we left in the ID column, but it still has a huge impact. So ID was just kind of a useless data column. Oh, that time we got 99% accuracy. Nice. Anyway, so that's that. Anyway, so we dropped the ID column because it's useless, and then our X's are just everything except for the class. So our features are everything but the actual label itself. The Y's are our label. We do the train test, call the classifier, train the classifier, and then test it. Okay, simple enough. So that is the theory and application of a support vector machine. Now we're going to break it down. So if you have any questions, comments, concerns up to this point, feel free to leave them below. Otherwise, stay tuned to the next video. Thanks for watching.